Hello, grade 9. So we are going to continue our chapter 7, which is resistors. All right. So these are the objectives that we will be covering this week. So you guys already know how to apply Ohm's law, but we're going to practice this more. And you will know the formulas for determining the equivalent resistance of a grouping of resistors. Let's see what that is. Before moving on to the application of Ohm's law, I want to go back to this because I wasn't very impressed the way you guys handled this exercise in the exam. So I want to talk about it again. All right, so we did verify Ohm's law experimentally before the holidays, before the vacation, and we came up with this graph, right? Plotting the variation of the voltage as a function of the current. All right, and we ended up with this pink straight line. And what is so special about this straight line, first of all, that it is an increasing straight line. You can see how it is increasing and it is not decreasing. And the other thing is that it is passing through the origin, 0, 0. All right. This curve right here, when it looks like this, when it is a straight line that is passing through the origin, we call it the characteristic current voltage of a resistor. So this is the characteristic curve, the current voltage characteristic curve of a resistor. All right. Now, how does it look? It is a straight line that is passing through the origin. Now, I did say here that it has a positive slope. Why am I saying this? Why? Because I will be explaining how we can actually find the slope of this line. To find the slope of the line, we need to pick 2 points on the line. All right, 2 points, any 2 points. So let's say I want to pick this point and I want to pick that point. The first point is of coordinates I1, U1, right? And this one I2, U2, because I is the abscissa and U is the ordinate. Then for me to find the slope, I need to find U2 minus U1 over I2 minus I1. Great. To make things easier for you, no need to pick 2 points. You can only pick 1 point, and the second point can be the origin, which is 0, 0. All right, so all I need to do is to pick 1 point. So let's say this one. Okay, so I is 0.1 and U is 10. So it is 10 over 0.1. We need to look at the units. This is in volt, this is in amperes. Great, perfect, no need to convert units. But if this is in milliamperes, I need to convert it to amperes before putting it in the slope. Okay, so yeah, that's it, 10 and 0.1. But what is the second point? I said we pick 2 points. We said the second point is the 0, 0. So you write minus 0 and minus 0. Okay? I know it doesn't make any difference, but I need to see it. And the answer is 100 ohm. All right? So this is how we can find the slope. And you can see that the answer, whatever the 2 points that you pick, you'll get the same slope, you get the same answer. So this is how we can say that U over I is actually equals to a constant, which is the resistance. And this is how we can come up with Ohm's law, where U equals R times I. I know we've seen this before, all right? So it's not something new, but I am, just mentioning it again, okay? So this is Ohm's law. Every time you want to use Ohm's law, you have to tell me that you guys are using Ohm's law. So you say, by Ohm's law, I use this formula. R is the resistance in ohm, I is the current in ampere, and U is the voltage in volt. All right. Now, this voltage is the voltage across the resistor. This current is the current that is flowing in this resistor, all right? We can put this relation in a triangle so that it's easier for you to come up with the rest of the formulas, all right? So you can see that U equals R times I, and you can see that R is equal to U over I, and also the third one is I equals U over R, all right? And these are the different units for the resistor, for the resistance, all right? Let's solve a few applications from the book. Okay, so you can open your book, page 79 to exercise 5. It says the current flowing in a resistor becomes 0.32 amperes. So I have the current. Okay, so this is I. If it is fed by a voltage of 16 volt, so I have the voltage across the resistor, U, and I have the current that is flowing in this resistor, I. It says calculate the resistance. All right, so I say Ohm's law. What does it say? Ohm's law. It says that U equals RI. All right, but I want to find the resistance. So R is equal to U over I, and that is 16 volt over 0.32 amperes equals to 50 ohm. Exercise 6, it says a resistor of resistance R equals 48 ohm carries a current I equals 25 milliamperes. Before moving on, I'm not going to keep the current like this because when I want to use it in Ohm's law, it needs to be in amperes. So let's convert it right now. So from milliamperes to amperes, what do? We divide by 1,000, right? So over 1,000, and that is 0.025 amperes. Part A, what is the voltage across its terminals? So I need to find the voltage. So by Ohm's law, U, the voltage, equals RI, and that is 48 ohm times 0.025 amperes, and that is equal to 1.2 volt. Part B, calculate the current if a voltage of 5 volt is supplied across its terminals. All right, so I need to find the current now. Okay, if a new voltage is supplied across its terminals. You guys know that the resistance of a resistor is one of its characteristics. Okay, so it does not change. So I have this as constant. I did change the voltage, U, and I will get a new current, but the resistance, it's like its name. Okay, it will not change. So also by Ohm's law, okay, so by Ohm's law, I have U equals RI, but now I need to find I. So I equals U over R, and that is 5 volt. This is the new voltage over the resistance, which I have 48 ohm, and the answer is 0.104 amperes. So moving on to the grouping of resistors. Now you guys know a resistor is an electric component that opposes the current in a circuit. And we've seen a resistor, it looks like that. All right, but what if I want to have like a group of resistors in a circuit? What if I want to have like 2 resistors right next to each other in series? What if I want to have 3 resistors in series? All right, so I could have that. Now what I want to do is to actually find the equivalent resistance of all these resistors together. So instead of putting 2, 3, 4 resistors right next to each other, I can put only one resistor with a resistance equivalent to all these 3. All right, so as if this one resistor, okay, like this equivalent resistor, it can replace a group of resistors while producing the same effect. First of all, we're going to start with the series grouping. From the word series, it means that the resistors will be grouped right next to each other, connected in series. Let's look at this example right here. You have R1, the first resistor. All right, so I'm using an ohm meter to measure the resistance of this resistor, and I'm getting 10 ohms. Now, R2, the second resistor, its resistance is 15 ohm. All right, now I did put them right next to each other in series. I did connect them in series. So if I want to find the resistance, which is the equivalent resistance for both of these resistors together, I'm getting 25. So this is 10, this is 15, and this is 25. What do you think, guys? The equivalent resistance is equal to what? It is simply equal to the addition of both of these. All right? So the equivalent resistance of two resistors grouped in series is R1 plus R2. What if I have another resistor? Then plus R3. What if I have four resistors in series? Then plus R4. So I simply add them. The equivalent resistance of resistors connected in series, you simply add the resistances, okay? A little note here is that this R equivalent, since I'm adding things together, so this R equivalent will be larger than the largest resistance. You can see it right here. It is 25, which is larger than 10 and larger than 15. All right, so yeah. Now I want you to click on this picture right here so that we can go to the next slide. Now we've seen this before, how the cars are the current flowing in a circuit, the road is the circuit, and this little checkpoint is actually the resistor, and how it is not letting all the current pass through it. All right, so yeah, this is how a resistor works. It opposes the current. It resists the flowing of the current. Now I'm gonna add another resistor in series with the first resistor. You can see what is actually happening. The car or the current is taking much longer, right, to move to the other side. Why is that? Because I added two resistors right next to each other. So they are going to oppose the current more now because their equivalent resistance is simply adding both resistances together. See how? The current will be opposed more. Now, what if I did group two resistors instead of in series? I did group them in parallel, all right, just like this one. How can I find the equivalent resistance of both of these resistors connected in parallel? How can I replace them with one resistor of, a specific resistance? So let's see, the first resistor R1 of resistance 10 ohm, the second one 15 ohm. But when I group them in parallel, the equivalent resistance is actually 6 ohm. So I'm not adding 10 plus 15 the same way I did with the series resistors. What am I doing here? I want you to try to find something. Find me 1 over 6 and find me 1 over 10 and find me 1 over 15. Now try to add 1 over 10 plus 1 over 15. It will be equal to 1 over 6. So what is happening here? The formula for the equivalent resistance is actually 1 over R equivalent equals 1 over R1 plus 1 over R2. Now you might ask, what if I have R3? What if I have R4? What should I do? You simply add 1 over R3 and then you add 1 over R4 and then this are equivalent, all right? It is, you can find it using this formula. Okay, now in the case where I have only two resistors, I can use another formula. Let's look at it. So in case I have only two resistors, so I can find 1 over R equivalent equals to, I need to find a common denominator here. So it is R1 times R2. All right. Now let's see, R1 times R2 divided by R1. It is R2 times 1 R2. And then R1 times R2 divided by R2, it is R1 times 1, it is R1 plus R1. Okay, so R equivalent equals, if 1 over R equivalent equals to R1 plus R2 over R1 times R2. How about R equivalent? I simply find the reciprocal of this, all right? So it is R1 times R2 over R1 plus R2. And this is the formula where you can use right away. Okay, so you can use this directly only in the case of two parallel resistors. Now I will be adding another resistor in parallel with this one. All right, you can see that this one is not letting much current pass through it. But if I add two resistors in another resistor in parallel with the first one, you can see both resistors are working alone, all right, letting current pass through them. But since current is passing through both of them, all right, it means I have more current that is flowing outside, all right, flowing out of them. So the equivalent resistance of both of these resistors is actually less than the resistance of one resistor. See? So it is less. It is opposing the current less here. It is letting more current flow. So we're going to solve an application on that in your books, page 81, exercise 18. It says consider two resistors of the respective resistances R1 and R2. Calculate the resistance equivalent to the grouping of resistors in each of the following cases. So the first case, they are saying that R1 and R2 are connected in series. So when they are connected in series, then the R equivalent of both of these is equal to R1 plus R2. All right, so it is 3 ohm plus 6 ohm and equals to 9 ohm. That is it. Part B, it says they are connected in parallel. So in parallel, I can use two formulas. I can use 1 over R equivalent equals to 1 over R1 plus 1 over R2. Or I can use the other formula, which is R equivalent, since I have only two resistors, so I can use the next one, equals to R1 times R2 over R1 plus R2. Let's substitute. So it's 3 ohm times 6 ohm over 3 plus 6. Okay, and that is equal to 18 over 9, which is equal to 2 ohm. All right. Now we're going to solve this application. Okay, it's not found in your books. It says calculate the equivalent resistance of the resistors R1, R2, and R3 connected in parallel. So I have not only two resistors, I have three resistors connected in parallel. So guys, in this case, I can use R equivalent equals R1 times R2 over R1 plus R2. No, I cannot use it because I have three resistors and not two resistors. So which formula I can use? I can use the other one, all right, which is 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. And now we substitute 1 over 10 plus 1 over 20 plus 1 over 30, and you'll get 0.183. Now the question is this the answer? Is this the answer for R equivalent? No, guys, this is equal to 1 over R equivalent. Do not forget that, all right? This is a very common mistake. Do not stop here. This is not the right answer. So R equivalent is the reciprocal of this. So you put 1 over 0.183, and this is R equivalent, all right? So our equivalent is 1 over 0.183, and it is equal to 5.45 ohm. Now, there is a little note I want to mention here is that you can see in parallel connections, the R equivalent that you get is actually smaller than the smallest resistance. So it is smaller than 10 in this case. See, it is very small. So there is like one more thing I want to talk about in this chapter, which involves a voltmeter and an ammeter. So you guys know from before that I said that we can put an ammeter in a circuit right next to the lamp and it will not affect the voltage in this circuit, like it won't take any voltage. But why is that? Because it has zero resistance. All right, so this ammeter that we place in a circuit, its resistance is the same as any connecting wire, basically. So it has a negligible resistance, and this is why I can include it in a circle and it won't affect the voltage inside or the current in the circuit, all right? The other thing is that the voltmeter, once I connect a voltmeter in parallel across any electrical component, let's say a lamp, you guys, I told you before that the current, it cannot pass through the voltmeter. So the current reaches this point and then it continues through the lamp and it won't pass through the voltmeter. But why is that? We said it, but we never explained it. Because a voltmeter, it has a very large resistance, all right? So it has a very large resistance and won't let any current pass through it. This is why all the current will go through the lamp. So this is another thing. And yeah, that's it. We know that a connecting wire, it has a zero voltage and it lets all the current pass through it normally. And this is why, because its resistance is zero, same as the ammeter. All right, so I need you guys to remember these three things. They are really important. So the resistance of a connecting wire is zero, the resistance of an ammeter is approximately zero, and that of a voltmeter is very large, and this is why no current will flow through it. All right? And that is it. We are done with this chapter. I hope it is clear. In our live session, I'm gonna go, I'm gonna go over these ideas really fast and we'll start solving exercises from the book. All right, so I'll see you in the live session. Take care and bye-bye.